And what this does is and you've seen it in the tech assignment, it samples from a population and allows you to infer the population parameters based off of the sample statistics. So I'll show you an example of what it all means, but this is all textbook jargon here. You could read it, but I think between the tech assignment and what I'm about to show you, that you're probably better off with that, because most people look at it and say, okay, there's more formulas. You have this formula here and this formula here, and you know that's part of it. You know, pretty much everything we do involves a formula in some capacity. It's just knowing why the formula is important and how it works. That's really where we're at. So I'll take you through this example and also take this as a typo because I don't see the word example here. Makes it seem like it's part of the notes. Okay, so that's a typo for somebody. So we're given a population consisting of the numbers 1, 2, 3, and 4. We want to find the population mean, bolded population, so population mean and population standard deviation. So we'll do that first. So here's my population. I'm just going to write population. All right, the population consists of only the numbers 1, 2, 3, and 4. All right, what we want to do is find the population mean, which would be mu, and the population standard deviation, which would be sigma. Calculator can do that for us very easily. It's a small sample, so you may just want to go into the toolbox and go under statistics. All right, it's it's down further. Lists, statistics, and then you could find the mean and the standard deviation. Yeah, so that might be the way to go because it's just the numbers 1, 2, 3, and 4. So if I wanted to do this, I just select mean. So let me just make a note. So toolbox, lists, statistics. All right. So if I bring up mean, all I do is type in 1, 2, 3, 4. Syntax error. I was about to say that I've never actually used this function before, but I didn't say it because if it worked, I could pretend like I just know everything. But what happened is, since I've never used this function before, I just rolled the dice and I did not get a 7. Let's just put it that way. So I can try to troubleshoot this, or we can go back to the way that we know. Let me just try one thing first. Yep, you need the squiggly brackets. All right, so it would be, in this case, mean, squiggly, little squiggly jammy there. Then 1, 2, 3, 4. And as a result, we get 2.5. I mean, you're looking at the numbers 1, 2, 3, and 4, and you're finding the average. In theory, you probably shouldn't need a calculator for something like that, but we know that this is the rare instance where the numbers are actually nice. All right. So let's see if I can apply my newfound knowledge to the standard deviation. So into the toolbox, lists, statistics, standard deviation. Let's see, let me get rid of one of those. I got 2 open parentheses. I only want one of them. And it worked. Yay. It gives us the value in radical form too, which is nice. You know, if you don't want to worry about rounding. I mean, so I could write radical 5/2. And that's approximately 1.118. You know, we tend not to, when it comes to statistics, means and standard deviations, we tend to go in decimal form. But then, like if the calculator is going to give you the exact value, you might as well just take it, right? Because then you don't have to worry about making a rounding error. All right. So that's the population mean and the standard deviation. So now what we need to do is create a list of all possible samples of size 2. All right. So samples of size 2. So that's where n is equal to 2. From the numbers 1, 2, 3, and 4. All right. So what we do is we think about any possible way we could pair one number with another number from that population. All right. The trick is, because it's a complete sample space, it's possible that you could have repetition 1 and 1, because we're not given a scenario here. We're not necessarily saying, or we got 4 students that we want to put in groups of 2. Rangers School. Nice. Oh, it's Goodrow. Nice. So it could be 1 and 1, 1 and 2, 1 and 3, 1 and 4. It could be 2 and 1, 2 and 2. We learned in probability that ordering of values is important, not just the values themselves. You never know. The context may determine that you need to consider both orders, right? So 1 and 2 corresponding with 2 and 1, right? So 2 and 3, 2 and 4, 3 and 1. Oops, too close. Looks like a 31. 3 and 2, 3 and 3, 3 and 4, 4 and 1, 4 and 2, 4 and 3, 4 and 4. All right. So this is the list of all samples, all possible samples of size 2. For each sample, determine the mean. Right. So I'm looking for the average of each pair of values. So the average of the first 2, 1 and 1 plus 1 divided by 2 is equal to 1. Average of 1 and 2 would be 1.5. Same idea down the line. That's supposed to say AVG. It started looking like an AUG, like August. Not my intent. But now it really looks like AUG. Right, comma. Commas down the line. Close them up. And we're going to have to do the same thing with the next set in a sec. You do it now, or we'll figure out the averages first and then do it in a minute. 1 and 3 has an average of 2. 1 plus 3 is 4, divided by 2 is 2. 1 plus 4 is 5, divided by 2 is 2.5. 1.5, 2, 2.5, 3. Right, just adding the two numbers up and dividing by 2. All right, so same idea going down the next line. And what we're creating is what's known as a sampling distribution. This is a distribution of all possible sample means when the sample size is equal to 2. Just gonna relocate some things. There was a point when I had extraordinary handwriting, but then it all fell apart in first grade. I always talk about the guy who scored the goal. I mean, yeah, he made a good shot, but the pass from Lindgren going to him, that was the key to that play.
Professor, I just wanted to say I had to rejoin the meeting because my internet where I am right now is kind of spotty.
Gotcha. Not a problem. All right, so looking for averages again, just more and more. 3 and 1 is if you just look at the middle point between two numbers, because the median and the average, when only dealing with two numbers, they end up being generally the same, because you're splitting the difference between the two. So 2, 2.5, 3, 3.5, 2.5, 3, 3.5, and 4. Now this is a much bigger list. I actually have to resize a little bit so I can get, well, that looks terrible. Resize a little bit so I can get a little bit more stuff on the right hand side there. All right, so what I want to do here is create a list of the sample means. All right, but I notice that there's some repetition. All right, like the 1.5 occurs a couple of times. The 2s occur a few times, and so on. So I might want to make a frequency table out of this. All right, so I'll make a list of the X bar values, all right, because that's what all these things are. They're all X bars. They're sample means. We created samples from population, and then we found the mean, so sample mean. But I also want to indicate what the frequencies are that correspond to that. So the 1, I only see 1, 1. 1.5 occurs twice. 2 occurs 3 times. Let me get some more highlighter in here. Green is up. 2.5 occurs 1, 2, 3, 4 times. Three occurs 1, 2, 3 times. It looks like we're developing a little bit of symmetry here, because the 3.5 occurs twice. Let's go that light red there. And then the 4 only occurs once. All right, so this would be what we call a sampling distribution. Whatever. So it's a sampling distribution. It gives us, well, really the distribution of sample means. And so what I want to do is find some summary values related to this. I just wove right through the defense. So I could find the mean of this set of means. I could also find the standard deviation for this set of means. And then we'll see why we probably never want to have to do this again. Right? But if I go into the home screen, statistics, under data, I'm going to just clear out what I have here. Put these values in, 1.5, oh, sorry, 1, 1.5, 2, 2.5, 3, 3.5, 4, and then adjust the frequencies accordingly. 2, 3, 4, 3, 2, 1. All right. And for giggles here, I'm going to go ahead and throw in the original population while I'm here. All right. That original population had values 1, 2, 3, 4. All right. And we'll just do a quick side-by-side comparison on the graphs. So looking at the histogram, I can clean up the spacings here a little bit. I'll go to settings and make the bin width 0.5. I don't know that that's precisely a normal distribution, but it sure looks like one. It's got symmetry. It looks like it has the right general shape. You know, maybe it's not, but it's more likely to be a normal distribution than this. Right? This is a uniform distribution. All right, the ones, the twos, the threes, and the fours all occur the same number of times. One occurs once, two occurs twice, once, three occurs once, four occurs once. All right, but we've created a normal distribution, and we were talking about normal distributions in the last part of the unit with all that norm CDF stuff. So now I have the means to take a data set that's not necessarily normal and make it into a normal distribution, right? That's the power of the central limit theorem. So I'll go to my stats here, and we're going to go for the population mean, right? The mu is equal to 2.5, and the sigma is about 0.791. All right. I left an exaggerated space there because it's not the population mean. It's the population mean of all, let me get a fresh color here, something purpley. It's the population mean of all of those sample means. So we call that mu sub x bar. It's also the population standard deviation of all of those sample means. When you look at a population itself, the distribution really is that these are the set of x values. So when we find a population parameter, we're doing that of the variable x. Same thing with the standard deviation. All right. If I actually wanted to, I'll just kind of go back. I mean, if you're writing this down, you don't have to write this part down. I just want to kind of drive the point home. Let me get rid of this. I can make a frequency table out of this. 1, 1, 1, 1. And you can see when I do that, aside from the fact that it's uniform because all the frequency values are the same, you can see that it's the mean referencing x. All right, the population mean referencing x. Whereas over here, it's the population mean referencing x bar. Let me get another color in here. I think I've kind of run the gamut here. Just go a little darker. All right, so this is x, and this is the population mean and standard deviation of x. Now, what we're trying to get at is how these two things are related. All right, so the central limit theorem, it's written above, but it's telling us that the population mean of the random variable x is always going to be equal to the population mean of all of the sampling distribution of all samples of size n, whatever the n is, in this case 2. The relationship between the standard deviations is not as clear, but since it's written right here, we can kind of just go with that. So sigma sub x divided by the square root of n is actually going to be equivalent to sigma sub x bar. All right, so the sigma coming from this distribution here is going to have that relationship with the mean and standard deviation from this distribution over here. All right, it's just we tend to write the mu because it's understood that it's of the random variable x. So we tend to write it as mu instead of mu sub x. You know, we have all these subscripts all over the place. You know, like why include one when you don't need to? All right. So we just generalize this to mu is equal to mu sub x bar but we usually write it the other way because that's usually the thing we're looking for, is equal to the population mean, and sigma sub x bar is equal to sigma over the root of n. All right. Now, I haven't really justified that that is actually the case, but up here, I mentioned, let me just go with a different color pen here, that n is equal to 2. All right. I indicated that the n value is equal to 2. So if I were to take sigma, which we discovered to be 1.118, and divide it by the square root of 2, get out of here, about 1.118. We know it's not precisely that, but close enough. Oh, that's not a 2. Fat finger strikes again. We get about 0.791, which is what this value is over here. All right. And so that's the important part of all of this. We already knew that the mean was going to be 2.5. That's the important part of all of this, because what this is telling us is that we don't have to do all of this stuff anytime we want to know what the mean of a sampling distribution is going to be. All right. That's really important because what did we have? We had a total of 16 possible outcomes. When I took the population of numbers 1 through 4, we had 16 possible outcomes. But what if I wanted to know samples of size 3? I'd have to come up with every possible arrangement of those 4 numbers. So it could all, maybe it's all 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 1, 4. 1, 2, 1, 1, 2, 2, 1, 2, 3, 1, 2, 4, 1, 3, 1, 1, 3, 2, 1, 3, 3, 1, 3, 4. And then we'd move on to the 2s and then on to the 3s. Eventually you notice the pattern, you kind of get to the shortcut, but it would take a little while. And also, the original population only had 4 values in it. What if the original population, even if I only wanted samples of size 2, what if the original population had 25 values? Okay, I mean, that's going to be a lot. Okay, because really what we got here is 4 to the second power. That told us how many samples we would have. So that's our 16 samples. 25 to the second power is 625. You'd have to indicate 625 different possible outcomes, and then find all the averages of each, and then, and then all the stuff that we just did. All right. So I did it with a very small example to kind of prove the point, but now we could just rely on formulas. Okay, because we know that the formulas are going to work. Or at least we demonstrated to ourselves that they'll work. All right. The first example on the next page, find the probability that the score is above 140 given 143 and 29. All right, for the mean and standard deviation. This one I say is not central limit theorem. All right. So it's like, oh, we just did all that stuff with central limit theorem. Why are we not doing an example that involves central limit theorem? I want to show you how 2 similar looking examples, 2 similar looking problems, I should say, could lead to different approaches. All right. So we want the probability that the score is above 140, given that the mean is 143. 143 smack in the middle. And the standard deviation is 29. So 143 minus 29, just to get us our first tick mark, 114. We want above 140. That's really all I have to label, because now I know that the 140 has to be somewhat close to the 143. And I'm looking for this area. All right. So probability that X is greater than 140. That's gonna, we could do it a couple of ways. The way I think I showed you last time is the norm CDF range. There's 2 ways to do it. Norm CDF range, where we start off with the 140, we'd eventually get to infinity if this were not a finite branch of math. But the function itself goes to infinity. We can't put infinity in there, so we put something large. And then the mean and standard deviation. So this is the A value. So quote unquote A. This is the mean. Oh, nope, sorry. That is what it is. It's large. This is the mean. And this is the standard deviation. Close it up. Go to our toolbox. Probability, distributions, normal. Okay, same place we got it before. Norm CDF range. Oops. 140. Something large. I mean, I don't know what the context is here, but I got to figure large is going to be something substantially bigger than 140. Right, so maybe 1,000. The mean of 143, the standard deviation 29. And we get this decimal here about 0.541. All right. Now, I chose a large value of 1,000. I don't know if I went large enough until I do the computation again with a number that's even bigger. There should be no change in the decimal outcome. Right? If the decimals are the same, then you've gone far enough. So we're satisfied with the 0.541. Also, when you look at the graph, I mean, we didn't shade a whole heck of a lot more than half of it, but we did shade more than half of it. 0.541 is more than a half. So that's consistent. All right. So that's where we've been. Now we're going to go on. The probability that the mean score, all right, so the mean score, key term there, is above 140, and then they give us an n value. All right, that's a sample size. All right, so what this is telling us is to find the probability, not that x is greater than 140, but that x bar is greater than 140. All right, that's what this is. It's the x bar, the mean of the sample. The mean of samples with size 100, to be more precise. All right. But in order for this to work, I got to come up with a graph. Yeah. But I need to not, and I don't need to know the mu and the sigma. I need to know the mu sub x bar and the sigma sub x bar. The mu sub x bar is going to be the same as the mu. The sigma sub x bar is going to be whatever the sigma was divided by the square root of the sample size. So sigma sub x bar is going to be 2.9. All right, so I'm going to label up the graph again, but this time, even though I'm going to still label in the middle with 143, I'm going to increment out in terms of incremental values of 2.9. I know that's a little redundant, but I got there eventually. 143 minus 2.9 gets me to 140.1. All right, so that's going to be right here. All right, we can just assume that the 140 is just going to be a smidge to the left of that. But now I want this area. All right, so a lot of the numbers are the same here, but I definitely have more of the graph accounted for. All right, so norm CDF range, and in fact, it's really just all this stuff again. Right, except it's mu sub x bar and sigma sub x bar, and it's not 29 anymore. Now it's 2.9. I mean, statistics is a weird thing because we go through all these formative ways of learning the material, like let's learn why things work the way they do. But ultimately, when it comes down to it, you're going to be like, all right, well, what's the difference between this kind of problem and the one we just did? Here, we divide by the square root of n. Right? This thing is the only difference between the computations for something that's not normal distribution and something that's not central limit theorem and something that is. All right, so I'm just going to tuck a little decimal point in there. Now, you're not always dividing by 10 because, square root of 100 is 10. You're not always dividing by 10. So don't get the idea that all you got to do is slide a decimal place over. Sometimes, yes, but most of the time, no. All right. So you might, it might be an ugly number, but you do have to compute it. So about 0.850. All right. So that's a big jump in probability. Again, it was find the probability that an individual score is above 140 versus find the probability that an average score of a group of 100 individuals will be over 140. Right. Depending on the scenario, that may be much more likely, maybe much less likely. I just kind of look at it like my classic example for central limit theorem is if I were to walk into a classroom and ask myself, all right, I need one A student. I need to find a student whose average is in the A range. I could easily do that. Show of hands, is your average in the A range? Okay, so that's one thing. You get a probability, maybe half the class, so 50%. All right. But then what if I were to say, all right, I want 5 individuals whose averages together give an A. All right. So maybe one person's got an 80, one person's got close to 100, one person's a little below 90, one person's a little above 90, a couple other people are in the 90s. You'd have an average that's in the A range, right? But which is more likely to happen? And that depends on the nature of the class, depends on what the scenario is, but you would expect that there would be a substantial shift in probability, because like to get a group of A students selected at random, that's the key ingredient, because in classes, it kind of works out that way pretty frequently, where it's like, all right, who are the people who are going to work hard, like in-person classes, who are the people that are going to work hard? All right, let's all form a study group. That study group compared to other study groups, that's what central limit theorem is talking about. All right. And it's a weird concept, but it's very, very powerful. Another example of it, hopefully something a little bit more relatable, although I don't even know how relatable this one is. Math professors have IQs that are normally distributed with a mean of 125 and a standard deviation of 1.2. All right, so it's saying the mean is in the neighborhood of 125. Now, just for transparency, when I created this example, because it's fictitious, I made it up, but when I created it, I had in mind that IQ tests normally have a mean of 100 and a standard deviation of 10. Right. So, and we know from previous studies that if you're more than 2 standard deviations above the mean, then you're in the unusual category. So in terms of IQ, if you're unusual on the high side, it means your IQ is unusually high. All right. So I'm saying here that the IQs are normally distributed with a mean of 125, but only a standard deviation of 1.2, which means there isn't too much variation from math professor to math professor. All right. Whether or not that's true, well, we all have our own opinions. All right. So I want to know probability that an individual selected at random is going to have an IQ that's greater than 127. So actually is going to be greater than 127. All right, so I'm incrementing by 1.2, so this would be 126.2. This would be 127.4. And I guess with that in mind, I don't really need that tick mark because I'm looking for greater than 127, which would be around, yeah, I guess around right there. So this little tiny sliver of area. All right, so that's what we're going to find. And, you know, like, I mean, this is sort of tongue in cheek, but the idea was like, all right, if the real population has a standard deviation of 10 and math professors are already in the unusually high range, then we're all incredibly smart. You know, that's one aspect of it. But the other part of it is saying, all right, so if you're, because this is around 2 standard deviations away from the mean, if you're unusually smart for the human race and you're in this cohort of other people who are unusually smart, and then within that group you're borderline unusually smart, you know, a second level of being unusually smart, then you'd have to be, you know, really smart, substantially, you know, significantly, maybe even statistically significant, right? But again, it's norm CDF. Sorry, norm CDF range 127 to something large with a mean of 125 and a standard deviation of 1.2. So norm CDF range 127. I'll go to 1,000. I mean, contextually, if we're talking about IQs here, yeah, 1,000. I mean, if 120 is already unusually high, 1,000 is going to be nowhere near possible. So we have this number 0.0478. I give it another look with an even larger max value. Same decimal. Now, if there's a natural cap, you know, like if you happen to know, I mean, I don't know enough about IQ scores. I used to like, I remember the ones like those weird pencil paper tests that you take in elementary school with like this, you have a triangle, a square, a pentagon, a square, a triangle. What would be the next 3 elements of that pattern? You know, things like that. But, you know, like in terms of a real IQ test, I have no idea. So, but let's say the most you could ever get is like 150. You know, maybe that's the highest score that you could possibly get. Then my large number wouldn't have to go as high as 1,000 or 10,000. You just cap it off at 150. You know, so if there's a natural max, just go with that. Same thing with a minimum. All right. Now, in the next part, find the probability that 75 math professors, so that's an N value, randomly selected have mean IQs, so that's X bar greater than 127. So same structure as the last question, just with an X bar. And you know, like I did before, all the stuff here is going to come along for the ride, except we're going to have to swap out that 1.2. All right. So I need my mu sub X bar. My mu sub X bar is the same as whatever mu was. In this case, the mu is 125. The sigma sub X bar is equal to the 1.2 divided by the square root of n. So divided by the square root of 75. And in fact, that's what I'm going to type in here. 1.2 divided by the square root of 75. All right. But I'd like to have a sense decimal wise of what this value is over here. So the 1.2 divided by the square root of 75 It's roughly 0.139. Right, so that's giving us a spread value that's much smaller than it was before. Right, it doesn't seem like it's much smaller, but in terms of as being a fraction of the original population standard deviation, going from a 1.2 to a 0.139, that's a pretty massive shift, right? And it's even more illustrated when you start labeling the graph. You start off with 125 and you want to go out 0.139. That gets you to 25.139. I'm sorry, it should have been 125, but you get the idea. I just lost 100. All right. Then if I want to increment it by another 0.139, 125.278, maybe another 0.139. We're not getting anywhere near that 127 anytime soon. All right. I'd have to keep adding over and over and over again before I even got to the neighborhood of 127. So I did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I think 14 standard deviations is what it would take to get us to 127. All right. So when you see me not labeling anything further, it's not because I'm forgetting to do it. It's because it's irrelevant. Because if I try to get 127, it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'd be in this neighborhood over here. Like, how am I going to illustrate the area to the right of that? I'm not going to be able to. All right. But it also gives me a clue that the probability is going to be minuscule. All right. So I'll crunch the numbers. Let me go clear. I want to, how do you do it all in one shot? There we go. 127, something big, mean 125, standard deviation 0.139, or you could just put in the 1.2 divided by the root of 75. It's going to say 0. All right. It's not really 0. It's just practically speaking 0. All right. So it's saying that the probability is so low that it would be virtually impossible. All right. So we would say that this is virtually 0, which would also imply, so therefore, virtually impossible. Right. It's not, and unless there's some context that makes you believe this, it's almost never going to be exactly equal to 0, because there is the possibility that if you go around sampling math professors, there's enough of them that you can find groups of 75. Maybe you'll find one entire group of 75 math professors whose average is above 127, average IQ. Right. I kind of look at it like, well, it's hard enough to find one. Okay. So one person who's brilliant, only 5% of the population, 0.0478, 0.0478. So if it's that hard to find just one, how on earth am I going to find a group of 75 of them?